what Rolle's theorem is saying to us, if you have a function f, if f is a function that is f is continuous, has to be continuous, no holes in it, on the closed interval from A to B. So if it's continuous on that interval and differentiable, which means you can take the derivative of it, on the open interval from A to B, that means you can take the derivative anywhere on that from A to B, not including the endpoints. And if f of A equals f of B, if all these conditions are true, three conditions, let me highlight the three conditions. The function is continuous, that's condition one. The derivative exists, and f of A equals f of B. Three conditions. If you can satisfy the three conditions, there must be. So it says then there is at least one number, you could have more than one, between A and B, we'll call it C, in the interval of A to B, somewhere between A and B, there's at least one number where the derivative of that the derivative at C is equal to 0. Huh?
Isn't that like almost the same as the intermediate value theorem?
Well, they don't have to equal intermediate value theorem. Yep. So now, let's take a picture. Draw it any way you want to. I can draw my function. Remember, you got to be, if to be the derivative exists, you can't have sharp edges in it. So I can draw it any way I want to, and I stop there. Is this function continuous from A to B? This is B. Do you see any holes in that function? You can do any function any way you want to. I don't see any holes in it, so it is continuous. Does the derivative exist? The derivative is the slope of the tangent line. Yes. The only time you can't have a derivative when you have a V shape. That's not the case. So there is a derivative here for every point from A to B. F of A equals F of B. They have the same height. What this one is saying, there has to be at least one point, one value between A and B where the derivative is 0. I'm looking at that. I see more than one. I see this one. Remember, the derivative is 0 means what? Slope of the tangent line is 0. It has to be horizontal. There's one, there's another one, there's another one. You have 3 min-max points right there in this picture. You can sit all day long trying to think of different pictures. How can I make it where it doesn't work? What about if I do a straight line? Go ahead. This is A. This is B. It's continuous, like f of x equals 7. Can you take the derivative 7? 0. Yep, the derivative exists. Are they equal to each other? Yes. There has to be at least one point between A and B where the derivative is 0. Pick any point on that. Any point you want to, the derivative is 0. Why? Because the slope of the tangent line is the line itself for every point on that. I'll probably spend hours trying to come up with some picture. You say, what about this one? I said, okay. Is your function continuous here from A to B? Yes. Does the derivative exist? Not at this point. That's a V, upside down V. I can't use Rolle's theorem here. Don't even waste your time. Because there's three conditions you have to satisfy. The function is continuous. There's a derivative for that function from A to B. F of A equals F of B. If all three are yes, yes, and yes, there has to be at least one point there between A and B where the derivative is equal to 0. This one does not fit. Can't use Rolle's theorem. No derivative at that point. Does not exist. The derivative has to exist for every point from A to B. Different picture. Is this function continuous? Yes. From A to B? Yes. Can you take the derivative of that? Yes. I don't see any sharp edges in it. Is F of A equals F of B? The endpoints are the same height? Yes. There has to be at least one point between A and B where the derivative is 0. And that point is right here. That's where the derivative is 0. So what are they going to do mathematically? They're going to say prove Rolle's theorem. So let's take an example. Here's an example. Let's take this one. F of x equals x squared minus 3x plus 2. And I want to test that from 1 to 2. Well, this is a quadratic equation. We know it's continuous. Yes. Test number 1 passed. How about the derivative of that? 2x minus 3, is that continuous? Continuous. That's a straight line. So the derivative exists. I should say exists instead of continuous. Is f of 1 equal to f of 2? What's f of 1? F of 1 is 1 squared minus 3 times 1 plus the 2, which is what? 0. What's f of 2? 4 minus 6 plus 2, which is what? 0. Does f of 1 equal to f of 2? Yes. So all three conditions are yes, yes, and yes. Rolle's theorem says there has to be at least one point between 1 and 2, between these two numbers, where the derivative is 0. There has to be. So take your derivative, set it equal to 0, and see where that value. 2x will have to be what? 3? What's x equal to? 3/2. Is that between 1 and 2? Yep. And the derivative at that point is 0. So that's the kind of work you have to do. You got to find that point and verify it's between 1 and 2. And the derivative is 0. I'll take another one. Again, sometimes you have more than one. You could be 2 or 3 values, but at least 1 point. Again, if you graph this one, if you went to your calculator and you graph that one, the graph will look like this. This is the 1, and this is the 2. There has to be 1 point where the derivative is 0, and that's right here. What is it? Minus 1, when you factor, give me 1 and 2, right? Yeah. I don't know how low it goes down, like when it's 3/2, might not go that low, but the graph should be very similar to this, what I drew there. That's the 1 and the 2. Let's see, y equals x squared minus 3x plus the 2. And let's set my window, I don't know, from -3 to 3. The y value, I don't know, we'll do -4 to 4. I still want to use the same value. I want you to think it has to be the same value. And graph it. Quit. Window. Or -3. There's the 1 and the 2. See how it dips down? And the derivative right there will be this horizontal line. I might even ask you that on the test. Tell me where is the horizontal line equals to 0. Or they have a tangent. The slope is tangent. How do you find out where the slope is tangent? Or the tangent line is horizontal, that's what I meant to say. The tangent line is horizontal. Isn't that where the derivative is 0? Because the slope of the tangent line is the derivative. It says the tangent line is horizontal, like this. That means find out where the derivative is 0. Let me try another one. And let's go from -2 to 2. Is this function continuous? Should be. The only time you'll have discontinuity, or 90% of the time, is what? When you have division by 0, or you have the square root of negative numbers. There's no square root, nothing. Any value that you pick for x between -2 and 2, you will have an answer to it. What's the so it is continuous. That's test number 1. What about the derivative of that? Isn't that 4x cubed minus 4x? Does the derivative exist? Is there a value between -2 and 2? If you plug it into the derivative, you will not have an answer? every number between -2 and 2, open interval, if you plug them in, you will have an answer for the derivative. So test number 2 passed. The function has a derivative. What's step number 3 or condition number 3? Is f of -2, does that equal to f of 2? If that's a yes, we met all 3 conditions. F of -2, when you do that, is that 16 minus 8, which is what? 8. What's f of 2? 16 minus 8, that's also an 8. So they are equal to each other. Yes. Now the Rolle's value theorem says there has to be at least one number between the -2 and the 2 where the derivative is 0. At least one number. We're actually going to get 3 of them here. Take your derivative and set it equal to 0. Forgot to turn the computer on. Take the derivative and set it equal to 0. Factor 4x out. What do you have left? X squared minus 1. Can you factor x squared minus 1? Isn't that the difference of 2 squares? You're multiplying 3 things, your answer is 0. That means one of them is 0. X minus 1 equals 0. That means x equals to 1. X plus 1 is equal to 0. X will have to be -1. All 3 of them are between -2 and 2. Again, if I graph this function, this is what my graph will look like. It will look like this. This is the -2 and 8. So the -2 might be like here. We have 3 values where the derivative is 0. This is one of them. That's the -1. This another one, that's the 0. And this is the 1. You have 3 min max. You have 2 min, 1 local max. These are absolute min, the smallest y value of the entire graph. This is a local max, the largest value in this neighborhood, relative or local max. Absolute means the entire graph. So when it's absolute min, that's the smallest y value of the whole graph. And these 2 are. But that's not the absolute max. That's not the largest y value. This value here is bigger than it. This value is larger than that one. This value is larger than this. These 2 endpoints are your absolute value. They are the biggest y value of the whole graph, but this is a local or relative max. So notice here the Rolle's theorem says we have at least one number, at least one. We found 3 of them. Again, if I ask the machine to graph that from -2 to 2, y equals, here we go, clear that, x to the 4th, x to the power of 4, minus 2x to the power of 2. And let me change the window now from -2 to 2. I know the y value goes as high as 8, as low probably when it's 1, -1. So I'll go from -2 to 8. There's my graph. And you can see there's a minimum value here, there's a maximum, there's a min. The topic today was Rolle's theorem and the mean value theorem. So we figured out Rolle's theorem. Let's see the mean value theorem. It's very similar to this. You're going to see it's almost the same thing with the exception of one step. You're not going to see f of a equals f of b here for the mean value theorem. So let's look at that. Mean. What does the word mean means? Average, yeah. So again, if f is continuous, on the closed interval, just like the other one, a to b, and the derivative exists there too, and you can differentiate that. Differentiable on the open interval. From a to b. Notice here's the difference right there. This one, f is continuous, same thing, exactly the same thing. On the closed f, I forgot to write f. If f is, I left the function f. If f, oh God, squished together. If f is continuous. So just like the other one, f is continuous, f is continuous. The derivative exists, differentiable. This one does not say f of a has to equal f of b. It could be, but it doesn't have to be. So then, there has to be, there is at least, I'll say exist, a number we'll call C, which is between A and B, such that the derivative at C will equal 1. Here's why I write it, 1 over b minus a. I'll change it to our book. Our book doesn't write it this way. Of f of b minus f of a. Our book writes that f of b minus f of a over b minus a. Sometimes I write it this way, and other days I write it like that. Couldn't tell you when. Just depends what mood I'm in. Either one, it's the same thing. So let's take an example and see how that works. Example. Here's f of x, 5 minus 4 over x. And I want to test it from 1 to 4. I couldn't go from 0. How come I didn't write 0? I said 1 to 4. Because if you write 0, what's 4 over 0? Undefined, the function is not continuous. This is a straight line. It has a y-intercept of 5 and a slope of, oh no, I have x on the bottom. My mistake, no. That's not. If it was x over 4, yes, I was thinking x over 4. I go y-intercept of 5, x equals 1, the slope 1/4, but the x is in the bottom. So if I graph that, it's not a straight line. Five minus 4 divided by x. And that's it. My window, I want it to go x equals 1 to 4. The minimum value is 1. Maximum value is 4. And I have no idea how high it's going to go. I'll go -8 to 8. Let me change the one just to see what it looks like. Curiosity bugging me now. Let's go -4 to 4. Wow. See, that's right. I don't know if you can see it. I couldn't go from 0. You can see there's a hole in it. So if you graph that, from 0, it goes like this. I'm interested from 1 from here to here. This is the 4. This is the 1. That's the part I'm looking at. There's another part to it that looks like this. But I'm only studying from this point to that point. I really could care less about this section. Is my function continuous from 1 to 4? Is f of x continuous? Yes. From 1 to 4, it is continuous. I don't care about the 0. How about the derivative? How do we take the derivative of that? Well, I can write that. What's the derivative of 5? 0 minus. I can write that 4x to what power? -1. 4x to the -1. What's the derivative of 4x to the -1? -4. That will make that a plus x to the -2. Which is 4 over x squared. You can see this derivative does not exist as 0, but I'm not studying the 0. I'm going from 1 to 4. Any number between 1 and 4, the derivative exists. So the derivative is there. So I don't have to worry about that. So we met the conditions. The mean value theorem is it has to be, there must be at least one point between 1 and 4 where the derivative equal to that number. Let's see what that number is equal to. What is f of b minus f of a over b minus a? B here is 4, so what's f of 4 minus f of 1 over 4 minus 1? F of 4, when x is 4, plug it in. 4 over 4 is 1. What's 5 minus 1? 5 minus 1 is 4. That would be minus. What's f of 1 when x is 1? 5 minus 4, that's a 1. So now what they're claiming, the mean value theorem claims there has to be at least, there must be at least one value, C, between 1 and 4, where the derivative at that point is equal to 1, whatever that number is. That's what they're claiming. There has to be. So let's see. We'll take the derivative and set it equal to 1. And solve it. The 1 is 1 over 1. We can cross multiply. 4 times 1 is 4. X squared times 1 is what? X squared. X will have to be plus or minus 2. I'm only interested between 1 and 4, so X will have to be what? 2. So at X equals to 2, the derivative is equal to 1. The slope of that tangent line will be 1. So if you zoom in on your picture there, just from 1 to 4, let's say this is the 1, this is the 4, I'm enlarging it so you get to see it. At 2 here, if you find the slope of the tangent line, the derivative here will be 1. X is 2, which is between 1 and 4. There has to be at least one number between 1 and 4 where the derivative is equal, in this case, to 1, whatever that number is. Now, a lot of people will have fun with this equation. I don't want to leave it without mentioning that. Notice if you look at that equation, see it? That's what they're saying, the derivative. Now, if you play with the math there, this is over 1. You can cross multiply. This times that is equal this times this. So you end up with what? F of B minus F of A equals B minus A times the derivative at C. Which means F of B equals F of A plus B minus A times the derivative at C. So you might see it looking like this. It's really the same thing. Okay. I said just 2 theorems in that section. I want to make sure we go over them. The difference between the mean value and the Rolle's theorem. Rolle's theorem, it says F of A has to equal F of B. And the derivative will be 0. The other one, the mean value theorem, F of A does not equal to F of B, and the derivative is not 0. It's equal to this value, F of B minus F of A over B minus A. In case you wonder what this value is, let me just look back at that picture. Trying to leave it and I keep coming back to it. I'm going to enlarge the picture just a little bit more even for that problem. We said there has to be a point somewhere there between A and B. Where the derivative at C, what happened to C that doesn't look like C? C between A and B is equal to F of B minus F of A over B minus A. I want you to look at the right side. The right side, this is F of A. This is F of B. This distance here, isn't that B minus A? And this distance from here to there, maybe I'll use a different color for them. So this is B minus A. And this piece here, F of B minus F of A. When you divide them, what are you getting? Isn't that the rise over the run? And what you're getting is the slope of this straight line that connects them. That's what you're getting. M, the slope of that line. There has to be a point between A and B where the slope on that point equal to this one. That's what that means. The slope, one of these points, going to have a slope matches that slope. So you can look at it like graphically. Say, if I put it right there, the slope is the tangent line. They look like parallel lines now. Close to that. Could be more than one, but in this case, just one. I'll stop with this.